Good afternoon, everyone. This is the second session for the current electricity, right? With respect to the NEET 2024, right? So we'll be discussing second part of the current electricity chapter, right? And we'll be dealing with some of the expected questions for NEET 2024 and some of the previous year's questions as well, right? So we'll be beginning with this question. You can see here we have a circuit here, right? Where different resistors are in this combination, right? So the question is that all resistances in the diagram are in ohms, right? Find the effective resistance between the points A and B. So this is the circuit here, right? This is the given circuit, and in this circuit there are 2 points A and B about which we have to calculate the effective or the equivalent resistance of this circuit, right? Now by points A and B, we mean that we have to connect a battery, right? We have to connect a battery across the two ends of this across the two ends of these 2 points A and B, right? So any battery can be connected, and we have to solve this circuit, or we have to find the equivalent circuit or equivalent resistance across these 2 points A and B, right? Now you can see that in this circuit, if we look at this portion of this branch of this circuit, right? If we look at this branch of the circuit, you can see the 3 ohm resistor and this 3 ohm resistor are in series, right? They are in series. So their effective resistance will be nothing. Their effective resistance will be 3 plus 3, that will be 6 ohm, right? And this 6 ohm resistor will be in parallel with this 6 ohm resistor, right? This will in turn give us the effective resistance. That will be 6 multiplied by 6 upon uh, 12, right? Upon 12. So that will be equal to 3 ohm, right? That will be equal to 3 ohm. It means once again there will be a 3 ohm resistor, right? There will be a 3 ohm resistor in series with this 3 ohm resistor, right? It will give us 6 ohm equivalent resistance. That 6 ohm will be once again in parallel with this 6 ohm. It will in turn give us 3 ohm equivalent resistance. And this 3 ohm resistor will once again be in series with this 3 ohm resistor, right? So it will eventually give us 6 ohm resistance, right? And this 6 ohm will be in parallel with this 6 ohm resistor, right? And this will lead to the equivalent resistance till this point equal to 3 ohm, right? So final circuit will be like this. This will be a 3 ohm, right? This is 3 ohm, right? And this is 3 ohm, and across these two ends we have connected a battery, right? Now you can see here this 3 ohm and this 3 ohm is once again in series with each other, right? Their effective resistance will be nothing. It will be 3 plus 3, right? That's 3 plus 3 ohm, that will be equal to 6 ohm, right? 6 ohm resistance, and this 6 ohm resistance will be in parallel with this 3 ohm resistance, right? So the R equivalent of this circuit will be nothing. It will be 6 multiplied by 3 upon 9, right? That will be equal to 6 upon 3, that's equal to 2 ohm, right? So equivalent resistance of this circuit, complete circuit, will be nothing. That will be the 2 ohm, right? Or we can equivalently write this circuit equal to 2 ohm resistor here, right? And this is the battery here, right? This is the battery, right? So the effective resistance or the equivalent resistance for this circuit is nothing. That's equal to 2 ohm, right? Now let's move on to the next point, right? Now you can see it's a very important discussion here, right? In this diagram, you can see this is the circuit, right? We have drawn a battery of 10 volt, right? One end of the battery is at 4 volt potential, and another end of the battery is at potential V, right? The question asks that find the potential V in the diagram, right? So we have to find the potential of potential of the point B here, right? We have to find the potential of point VB, right? So we have to find the VB here. Now you can see here. So how will we find the potential VB? Potential VB, the potential difference between the two terminals of the battery is 10 volts, right? So what we'll do is that we will just replace this 4 volt with a battery of 4 volt, right? Battery of 4 volt, and connect the negative terminal of this battery with the ground, right? Connect this negative end of the negative terminal of this battery with the ground, right? So it means that this negative terminal of this battery will be once again at the 0 potential, and this point will be once again at the 4 volt potential, right? Now what we can do is that we can also replace this battery, right? This point VB with the battery here, right? With the battery here, and this will connect this point here with the ground, right? This point here with the ground. So this terminal will be once again at the 0 potential. Now what we can do is that now we can apply, the circuit is a complete circuit, right? We can now apply the KVL, Kirchhoff's voltage law, from ground to ground, because the circuit is a closed now. This is a closed circuit, right? We can connect, or we can apply the KVL here in this branch from uh, this point and to this ground, or we can say we can apply the KVL ground to ground, right? So you can see here, if we move from this direction along this path, right, you can see we will face the negative terminal of this battery here, right? That's negative terminal, right? So we'll write it as -4, right? We'll write it as -4. Then we'll face here the negative terminal of this battery here, that will be -10, right? And we'll face the positive terminal of this battery, right? That will be plus VB, right? Plus VB, that will be equal to 0, right? That will be equal to 0. So from here, VB is nothing. It's 4 plus 10. That's equal to 14 volts, right? So it means that the potential the potential at this point P will be nothing. That will be equal to 14 volts potential, right? We have just done one thing, that we have connected the 4 volt, replaced 4 volt with a battery of 4 volt, connecting the negative terminal with the ground. And at point B, we have replaced the VB with the battery potential difference VB and connected negative terminal with the ground, and then applied the KVL from ground to ground, right? So it encloses the loop, right? Or we have closed the loop, right? From here, applying the KVL, we got the potential at point B equal to 14 volts, right? This is one way, right? This is one way. Another way is that since the potential difference current is flowing from the positive terminal of the battery to the negative terminal of the battery, right? So it means that if this terminal is at 4 volt, then this terminal must be at 14 volt. Then only 14 minus 4 volt will give us the 10 volt, right? This is another way of looking at it, but this is the more I will say more concrete way of solving this circuit, because it will help us to solve multiple circuits, right? So question number 3, looking at the question number 3 here, you can see once again the same circuit is here. There is a resistor of resistance 10 ohm, right? The current of 2 ampere is flowing through it, right? The potential at one of the terminals is 3 volts, and the potential at another terminal we have to find, right? We have to find the potential at terminal B, right? We have to find the potential at terminal B. Once again, what we'll do is that we'll replace this 3 volt potential here with a battery of potential difference 3 volt, and connecting the negative terminal of this battery with the ground, right? And similarly, what we'll do here is that we'll just replace this VB with the battery, right? Or potential difference VB, and connect this negative terminal of this battery with the ground, right? Now you can see here, this circuit is a closed circuit, right? From ground to ground, right? We can apply the KVL, right? So this will be the direction of the KVL we'll be choosing, right? This is the direction of KVL we'll be choosing. Now once again, we'll face the negative terminal of this battery, right? Of 3 volts. So we'll write it here -3 volts, right? Then now we are moving along the direction of the current, so the potential drop across this resistor will be nothing. It will be +2 multiplied with the resistance, that's 10, right? Then we'll face the positive terminal of this battery, right? This is the positive terminal of this battery, so we'll write it as plus VB. That will be equal to 0, right? That will be equal to 0. So from here you can see here, the VB will be nothing. That will be equal to VB will be equal to, it will be 20 minus 3, that will be 17, right? 17, VB will be equal to -17 volt, right? So -17 volt will be the answer for this question, right? So the potential point P will be at a potential of -17 volt, right? So -17 volt will be the correct answer, right? Now the similar question was asked in your NEET exam as well, right? In one of the papers of a NEET exam, the similar type of question was asked, right? We'll discuss that as well. Now let's look at this more complex circuit here. Let's look at this more complex circuit here. Now in this question, we have been asked to find the potential difference between the two ends VA and VB, right? We have been asked to find the VA and VB, right? So we have to find VA minus VB, right? We have to find the potential difference between the points A and point B, right? So we have to find the potential difference between between A and B, right? Now what we can do here, we can once again use the same technique, right? We will just replace this. Let's suppose the potential here is VA and the potential here is VB, right? At this point, right? We'll replace this VA potential with a battery of potential difference VA, but connecting the negative terminal of this battery with the ground, right? Connecting the negative terminal of this battery with the ground. Similarly, we'll be doing the same here. We'll replace here with the battery of VB and connecting the negative terminal of this battery with the ground, right? Now you can see here, now once again, it's a closed loop from ground to ground. We can apply the KVL from ground to ground, right? From ground to ground, we can apply the KVL. Now applying the KVL along this direction, right? Along this direction. Now first we will face the negative terminal of the battery here, right? That will be minus VA, right? And then the current is along we are moving along the direction of the current in the 2 ohm resistor, right? In 2 ohm resistor, the current is flowing 3 amperes, right? It will be 3 multiplied by 2, right? Then we are facing the positive terminal of this 4-volt battery. That will be plus 4, right? Then once again the current in this will be once again 3 ampere, right? That is plus 3 multiplied by 2, right? Then once again we'll face the positive terminal of this battery, that's 2, right? Then we have the positive terminal of this battery, that is VB, right? That's VB, right? VB. That's equal to 0, right? That's equal to 0. So finally we have minus VA plus 6 plus 4, right? Plus 6 plus 2, right? Plus VB, right? That's equal to 0, right? That's equal to 0. So from here, it will be 12 plus 6, that's 18, right? 18. So minus VA plus VB is equal to minus 18, right? That's equal to minus 18, right? Or we have to find VA minus VB. So VA minus VB will be nothing. That's equal to plus 18 volts, right? Plus 18 volt. The potential difference between the 2 points and the potential difference between the 2 points VA and VB here is plus 18 volts, right? So plus 18 volts will be the correct answer for this question. Now looking at this question right here, this was the question asked in your NEET exam, right? This was the question asked in your NEET exam. You can see here, the question is that we have to find the potential difference between VA and potential difference between 2 points A and B. Let the potential here be VA and let the potential here be VB, right? Once again, we'll be using the same concept. We'll replace this VA with the battery, right? And connect the negative terminal of this battery with the ground. And we'll replace this VB here with the battery potential difference VB and connecting the negative terminal of this battery with the ground, right? Now applying the KVL, right? Now applying the cable from ground to ground, right? We can apply the cable from ground to ground, right? So we'll first of all face the negative terminal of this battery, right? Negative terminal of this battery, right? It will be minus VA, right? Minus VA. Then we are moving along the direction of the current, that will be 3 multiplied by 2, right? Then we'll face the positive terminal of the battery, that will be plus 1, right? And then it will be 2 multiplied by 1, right? 2 multiplied by 1, that's the current, 2 ampere of current through this 1 ohm resistor, right? And then finally we'll face the positive terminal of this battery VB, right? That will be plus VB, right? Plus VB. That has to be equal to 0, right? So from here, minus VA plus VB, right, will be equal to 2 plus 1 will be 3, right? And 3 plus 6 will be 9, right? So that will be equal to minus 9. Or from here, VA minus VB will be nothing. That will be equal to plus 9 volt, right? That will be equal to plus 9 volt. So plus 9 volt will be the final answer for this question, right? So VA minus will be equal to plus 9 volt. Now let's look at this question, similar question here, right? To some extent, say similar question here, right? Find current through 12 ohm resistor. You can see here we have a circuit here, right? Where there are 4 resistors and potential at ends of these resistors is given as 2 volt, 3 volt, 4 volt, and 15 volt, right? 15 volt. Now the question is how we will find the current through the 12 ohm resistor, right? What we can do is that in the circuit, we can apply the KCL, right? We can apply the KCL, right, for this circuit. Applying the KCL, let's suppose at this point is the junction, right? We do not know the potential about this point. If we know the potential at this point, we'll be able to find the current flowing through this 12 ohm resistor. We'll be able to find the current flowing through this 12 ohm resistor. Let's suppose I is the current flowing through this 12 ohm resistor, and we do not know the potential at this point. We'll just assume the potential at this point to be V, right? Now applying KVL at point P, right? Apply KVL, apply KCL, not KVL. Apply KCL at P, right? At P. So we'll apply KCL at P, right? So KCL says that the total sum of the current should always be equal to 0 at the junction, or we can say whatever the current is entering the junction, same amount of current must leave the junction, right? That's the Kirchhoff's current law, right? So the current entering the junction, that will be nothing, or the sum total of all the currents will be equal to 0. So we'll be applying KCL here, right? So V minus 15 upon 12 plus V minus 2 upon 6 plus V minus 3 upon 4 plus V minus 4 upon 8. So this is the total sum of current, right? That should be equal to 0, right? That should be equal to 0 at the junction point. So what you will do here, you know that now the only variable in this equation is V, right? You will just find the value of V from this equation, right? Value of V from this equation. Then the current through this resistor will be nothing. It will be 15 minus V upon 12. That's the current I through 12 ohm resistor, right? That's the current through 12 ohm resistor, right? So current through 12 ohm resistor can be found by applying the KCL here at this junction point P, right? From there you will calculate the potential at point P, right? If you get the value of potential at point P, you will get the value of potential difference between uh, the ends of this 12 ohm resistor, and you will find the current, right? Let's look at this question, right? So it's a very important question here. You can see here there is a battery. This battery is of 30 volt, right? And this is a 3 ohm resistor here. This is a 3 ohm resistor here, right? This is also a 3 ohm resistor here, right? And this is 6 ohm resistor here, right? And we have battery of 15 volts here, right? We have battery of 15 volts. Now the question is that in the circuit shown in figure, find the current through the branch PD, right? We have to find the current through the branch PD, right? There are two ways to solve this question, right? There are two ways to approach this question, right? Uh, the first way is to use the KVL, right? KVL, right? Let's suppose the current along this loop is I1, right? And the current through this loop is I2. You can use the KVL, right, to find the current through the branch PT, right? So you will be using the KVL here, right? So what you will do here is for the loop first, for the first loop, right? Let's suppose this first loop, this is the second loop applying KVL, right? For loop first, we'll be applying KVL, right? We'll be applying KVL, right? So we are first facing the negative terminal of this 15 volt battery. We'll write it as minus 15, right? So in the 6 ohm resistor, we are moving along the direction of this current. We will write it as 6 times I1, right? 6 times I1. And then in the 3 ohm resistor, we are once again moving along the direction of this current I1, right? Along the direction of this current I1, right? So we'll write it equal to plus 3 times I1, right? Plus 3 times I1, right? So the current here, you can see this current is moving in the downward direction, right? There are two currents, right? One current is in the upward direction, right? One current is in the upward direction. Uh, this is I1 flowing along this direction, and this is the I2 flowing along this direction, right? The total current here has to be equal to I1 minus I2, right? I1 minus I2 multiplied by 3, right? That's equal to 0, right? That has to be equal to 0. So similarly, you can apply the KVL in the loop second, right? In the loop second as well. In the second loop, the KVL will be applied. We'll have the current I2 in the 3 ohm resistor. That will be 3 times I2. Will be facing the positive terminal of this battery. That will be plus 30 volt, right? Then we'll once again have the current 3 times I2 minus I1, right? 3 times I2 minus I1. That will be equal to 0. Now there are two equations. This equation first, and this is equation second. Now you can solve these two equations, right? By solving these two equations, you'll get to know about the value of the current, right? So that's how we can find the value of the current through the branch PT. This is one way of solving this question using the KVL. Another way is that that's a very smart way of doing this question, right? We'll try to do it in that way. Let's suppose we are connecting this point D here with the ground, right? We're connecting this point D here with the ground, right? It means the potential at this terminal will be 0 volt, and potential at this terminal will also be equal to 0 volt, right? Now this is the point here. This is the point here. We'll just assume the potential at this point BV, right? Now we'll apply the KCL at this junction point V, right? KCL at this junction point V. So applying KCL, it will be V minus 15 upon 6, right? Plus V minus 30 upon 3, right? Plus this is a 3 ohm resistor here, right? 3 ohm resistor. It will be V minus 0 upon 3, right? That's equal to 0, right? That's equal to 0. So from here we'll get to know about the value of V. So it will be V minus 15 upon 6 plus 2V minus 30 upon 3, right? That's equal to 0, right? Or we can write it V minus 15 upon 6, right? Taking 6 as LCM, right? It will be 4V minus 60, right? That is equal to 0, right? Or from here, we get the value 5b, 5b, it will be 5 will be equal to 75, right? That will be equal to 75. So from here, the potential V is nothing. That is 75 upon 5, right? 75 upon 5, right? That will be 15, right? That will be 15. That means the potential at this point is nothing. That's 15 volts, right? 15 volts. If potential at this point is 15 volts, right? So the potential difference between these two ends, B and D, is nothing. So potential difference here is, or we can say the current flowing through this branch will be nothing. It will be current I, right? That's the potential difference across the two ends, right? The potential difference is 15 volts upon the resistance. That's 3 ohm. That's equal to 5 amperes, right? Or we can say the 5 ampere current will be flowing through this resistor, right? So this is the way of solving this question. Apart from using the KVL, we can just ground the point D here, and the potential at the terminals will become 0. We'll just apply the KCL at the junction point to calculate the current through the given branch, right? The similar question is here also, right? Figure shows three resistances are connected with switch S, right? You can see here we have three resistances which are connected with switch S, right? Switch S. Initially, the switch is open. When the S is closed, find the current through it, right? Now you can see here we have this 20 volt potential here, right? At this end, 20 volt potential. We have this resistance of 2 ohm, right? So we have this resistance of 4 ohm here. This is the resistor of 2 ohm here, and the potential at this end is nothing. That's 5 volts, right? That's the 5 volts, and this end of this battery is connected, or this end of this resistor is connected with the ground, or we can see the potential at this end will be equal to 0, right? Now we have to find the current passing through the switch. So when the switch is closed, there must be some current flowing through it, right? Let's suppose the potential at this point is V, right? What we'll be doing is that we'll just try to find out the potential difference between this point and this point, right? Then the potential difference upon the resistance of this resistor will give us the current flowing through this switch S, right? So the potential at this point V can be found by using the KCL at this junction point, right? So using KCL, it will be V minus 20 upon 2 ohm, right? Plus V minus 5 upon 4 ohm, right? Plus V minus 0, because this end here is grounded, right? V minus 0 upon 2, that will be equal to 0, right? So from here, I will get 2V minus 20 upon 2, right? Plus V minus 5 upon 4, that's equal to 0. Or uh, the value here will be, we'll take the 4 as LCM, then we'll get 4V minus 40 plus V minus 5, that will be equal to 0, right? So from here, 5V will be equal to 45, right? Or the value of V is nothing, that's equal to 9 volts, right? Value of V is nothing, that's a 9 volts. So we have the potential here equal to plus 9 volts, right? It's plus a 9 volt potential at the junction point. If plus 9 is the potential here, then the current through this will be nothing. It's the potential difference, that is a current I will be the potential difference, that will be 9 minus 0 on the resistance, that's 2. But the current through this switch will be 4.5 amperes, right? So the current through this switch is nothing. It's 4.5 amperes. So the 4.5 amperes will be passing, will be the current passing through this switch, right? 4.5 amperes will be the current passing through this switch, right? Now let's move on to the concept of charging and discharging of a battery, right? So what is actually the charging and discharging of a battery, and what is the terminal potential, right? So terminal potential is actually the potential of the battery when the current flows through the circuit, right? Potential across the ends of the battery when the current flows through the circuit. Now you can see here, this resistance we call here, this is the internal resistance, right? This is the internal resistance or resistance offered by the battery, right? So this is the internal resistance which is offered by the battery, right? And R is the resistance of the load, right? Uh, in case of charging, right, when the battery is discharging, right, the current flows from the battery, right? Current will flow from the positive end of the battery to the negative terminal of the battery, right? Now we can apply the KVL, right? We can apply the KVL in the circuit. Applying the KVL in the circuit, right? So applying the KVL in the circuit. So if we apply the KVL, we'll get the value minus E, right, plus I into R plus I into capital R, right? That's equal to 0, right? Now this potential across the two ends or terminals of this battery, right? terminals of this battery. That's VAB, right? This potential difference we call as terminal potential difference, right? This is called as terminal potential difference, right? So the potential difference across the two ends of the battery is what we call as terminal potential difference, and this potential will be same across the ends of this resistor or load resistor R, right? Or we can replace this IR here with VAB, right? VAB, that's equal to V terminal, right? That's equal to V terminal. So from here, the terminal potential of the battery is nothing, that's E minus IR. So the terminal potential difference or the terminal potential of a battery is nothing. It's always less than the EMF of battery while discharging, right? While discharging, when the battery is discharging, right? When the battery is discharging. So while discharging, the terminal potential difference is less than the EMF of a battery, right? It's equal to EMF of a battery minus I times internal resistance of a battery, right? Where R is nothing, R is internal resistance of a battery, right? It's nothing, it's internal resistance of a battery. This is nothing, this is the internal resistance of battery, right? So in case of while discharging of a battery, when the battery is discharged or the battery is discharging, then in that case the potential terminal potential is less than the EMF and is equal to EMF minus I into R. Here R is the internal resistance of the battery. Now let's look at the charging case, right? When the circuit or battery is charging, right? When the battery is charging, right? When the battery is charged, then the direction of the current is from the negative terminal of the battery to the positive terminal of the battery, right? So we can say the current enters the positive terminal and leaves the negative terminal, right? So this is the direction of the current in case of charging of a battery, right? Now once again we'll apply the KVL and let's try to find out the terminal potential difference of a battery while the battery is charging, right? Terminal potential difference of a battery while the battery is charging, right? So what we can do here is that what we can do here is you can apply the KVL in the second case as well, right? We'll apply the KVL, right? Now we'll first face the positive terminal of this EMF of this battery, that's E. We'll write it plus E, right? Then the current is flowing along this direction, right? So it will be plus IR, right? That will be plus IR, right? Okay, that's plus IR. So this is plus E, right? This is the plus E here. And this is the direction of the current. So we are moving along this direction, right? So we are moving along this direction. So this will be facing the positive terminal. This is the positive terminal, right? This will be plus E, right? And then the direction of the current along the internal resistance that will be plus IR, right? And now looking at uh, this resistor, right? The potential difference will be once again plus IR, right? It will be plus IR. That will be equal to zero, right? That will be equal to zero, right? Now you can see here the terminal potential, right? The terminal potential in this case, the terminal potential VT here, it will be nothing. It will be E plus IR, right? It will be E plus IR, right? The terminal potential in this case, because IR is nothing, that's equal to terminal potential, right? That's equal to terminal potential VT. So you can see that while charging a battery, the terminal potential of a battery is greater than the EMF, right? And while discharging, when the battery is discharging, the terminal potential is less than the EMF, right? The terminal potential is less than the EMF, right? So this is how actually the things happen, or the how the terminal potential change while charging and discharging. So while charging, the terminal potential is greater than the terminal potential in case of discharging, right? So this is the battery, right? During charging and discharging, right? I will be applying the same concept here, right? To find the terminal potential, right? The in this circuit we have been asked to find the reading of voltmeter, right? We have to find the reading of voltmeter, right? In this circuit we have to find the reading of voltmeter, right? So what we can do here is that you can see this is the circuit here, right? We have to find the reading of the voltmeter. So there is a 20 ohm resistor, right? This is the 10-volt battery, right? This is the 10 ohm resistor here, and this is the 4-volt battery, right? So the potential will be actually potential measured by this battery will be the potential across these two ends, right? It will be the potential across these two ends. And we know that in this case, since voltmeter will assume that there is no current flowing through the voltmeter, right? So we'll assume there is no current flowing through the voltmeter. It means we can say the voltmeter is actually ideal voltmeter, right? Ideal voltmeter. So in case of ideal voltmeter, the current flowing is actually zero. So if in case of ideal voltmeter, the current flow is zero, right? We can apply the KCL to find out the current. It means the current through this circuit will be equal to zero, right? Through this voltmeter, and all the current will be flowing along this circuit, right? All the current will be flowing along this circuit, right? Now we'll find out the value of current, right? We'll apply the KCL along this circuit, right? We'll apply the KCL along this circuit. If we apply the KCL along this circuit to find out the current, right? So let's suppose the current is flowing I along this circuit, right? In this direction, right? I current is flowing, right? If this is the direction of the current, right? Or let's assume the direction of the current to be like this, right? Let's suppose this is the direction of the current, right? Now we can apply the KVL, right? So applying the KVL, right? What we'll do here is that we'll face first the positive terminal of this 10 volt battery, right? We'll write it as plus 10 volt, right? Then we'll face the current I across 10 ohm resistor, that will be 10 R, right? That will be 10 I, right? 10i. Then we'll face the negative terminal of this 4 volt battery, that will be minus 4. Then we'll face the 20i potential drop across 20 ohm resistor, that will be equal to 0, right? So from here we will have 30i, right? That will be equal to 30i minus 4, right? Minus 4 plus 10, that will be plus 6, right? That will be equal to 0, right? The value of current here comes out to be equal to minus 6 upon 30, right? That's equal to minus 1 upon 5. So the negative sign here signifies that the current is actually not flowing along that direction. The current is actually flowing along this direction, right? This is actual direction of current, right? This is the actual direction of current, right? Actual direction of current, right? This is the actual direction of current, right? And the magnitude of the current is nothing, that's I is equal to 1 upon 5 amperes, right? 1 upon 5 amperes, right? This is the value of the current, right? Now we have to find the potential difference of the terminal potential measured by this voltmeter. So voltmeter will measure just the terminal potential, right? Voltmeter will measure just the terminal potential, right? So the potential difference measured by this voltmeter will be the potential difference across this terminal. Now you can see that this battery is actually, right? Now this battery is actually here, the current here is flowing along this direction, right? So for this battery, the terminal potential will be nothing. It will be equal to, let's suppose the total potential across this 10 ohm will be, the potential across this 10 ohm resistor will be equal to 1 by 5 multiplied by 10, right? That will be equal to 2 volts, right? That will be equal to 2 volts, right? It means the 2 volt potential will be across this 10 ohm resistor. The remaining potential will be across these two terminals, right? That means the potential are measured by this voltmeter, that's VA minus VB. That's the potential measured by this voltmeter, that will be 10 minus 10 minus 2, right? That will be 8 volts, right? So the potential difference measured by this voltmeter will be nothing. It will be equal to 8 volts, right? So the 8 volt potential difference will be measured by this voltmeter, right? Now let's talk about this question, right? Reading of meter, right? Reading of meter. And now you can see here in this circuit, we have this resistor of 2 ohm, 2 ohm, and 2 ohm here, right? And there is an ammeter, right? Connected here, right? So you can see we have the battery of 2 volts and 2 volts each here with internal resistances 2 ohm and 2 ohm, right? And we know in case of parallel circuits, right? In case of parallel circuits, if we have two batteries in parallel, right? If we have two batteries in parallel to each other, right? If we have two batteries parallel to each other, right? Like this. This is internal resistor R1, this is E1, right? This is internal resistor R2, this is E2. Then the equivalent EMF of these two batteries is nothing. It's E2R1 plus E1R2, right? Upon R1 plus R2. This is the equivalent EMF, right? And their equivalent resistance is nothing. That's equal to R1 R2 upon R1 plus R2, right? This is the equivalent resistance, equivalent internal resistance of the two batteries, and this is the equivalent EMF of the two batteries, right? Similarly, if we have n number of batteries, right? If the batteries are n number of batteries are in parallel, we'll find the equivalent resistance in case of parallel combination as E1 upon R1, right? Plus E2 upon R2 plus E3 upon R3 and so on, right? Divided by 1 upon R1 plus 1 upon R2 plus 1 upon R3, right? So this is the equivalent EMF, right? And the R equivalent will be nothing. That will be 1 upon R1 plus 1 upon R2 plus 1 upon R3, right? So this is how we find the equivalent resistance in case of combination of parallel combination of the cells, and the equivalent EMF in case of parallel combination of cells, right? Now we have the only two cells here, right? We have only two cells here, so the equivalent EMF will be nothing. Equivalent EMF will be nothing. It will be E2 R1 plus E1 R2. That will be 2 multiplied by 2 plus 2 multiplied by 2, right? Upon 4, right? That's equal to, okay, that's 4 plus 4, right? Or 8 upon 4, that's equal to 2 volts, right? So it means the equivalent EMF of these two batteries will be nothing. It will be equal to 2 volts, and their equivalent resistance will be nothing. It will be 2 multiplied by 2 uh, upon 4, right? That will be equal to 1 ohm, right? That will be equal to 1 ohm. It means that we can equivalently write this circuit. We can equivalently write this circuit like this. This is a 2 ohm resistor. This is ammeter, right? This is 2 ohm resistor. This is the ammeter, right? And we have this battery of equivalent EMF equal to 2 volts, right? And battery of equivalent resistance equal to 1 ohm, right? So this will be the final circuit. This will be the final circuit. So this is battery of 2 volts, right? And battery of equivalent internal resistance 1 ohm, right? Now the measurement will be done by this emitter, right? Now the measurement will be done by this emitter. Let's suppose I current is flowing through this emitter, right? Or I current is measured by this emitter. So this current I will be nothing. And this current I will be equal to, right? It will be the potential difference upon the total resistance, that will be 3 ohm, right? So 2 upon 3 amperes will be the current measured by this ammeter, right? 2 upon 3 ohms. So 2 upon 3 ampere will be the current measured by this ammeter, right? Now let's discuss this question number 11 here. In this circuit, we have two batteries, 5 volt, 2 volt each, right? 10 ohm. We have this resistor of 10 ohm resistance, right? And we have this resistor of X ohm resistance, right? These are the two terminals, right? A and B, right? And we have been given that VB minus VA is given as 4 volt, right? VB minus VA is given as 4 volt, right? VB minus VA is given as 4 volts, right? It means the terminal potential is given as 4 volts, right? Or we can say equivalent potential is given here as the 4 volts, right? For these two batteries, right? What we can do here is that we know equivalent potential for the two batteries, nothing. That's equal to E2 R1, right? It will be 5 multiplied by X, right? Plus E1 R2, that's 2 multiplied by 10, right? Upon R1 plus R2, right? R1 plus R2, that's 10 plus X. And that's equal to 4, right? That should be equal to 4. From here, 5X plus 20, that will be equal to 40 plus 4X, right? 40 plus 4X, right? So from here, 5X minus 4X will be equal to 20, right? That's equal to 20. Or X is equal to 20, right? So from here, the value of this resistance X is nothing, it's 20 ohm, right? So 20 ohm is the resistance of this resistor X, right? Now let's look at this question, right? It's a very important question, right? It's with respect to the series and parallel combination of resistors, right? Series and parallel combination of cells, right? The question is that 54 identical cells, each of internal resistance 3 ohm, right? There are 54 identical cells, each of internal resistance equal to 3 ohm, are connected so that they provide maximum current to a load resistance 2 ohm, right? Find number of cells in a row, right? So 54 identical cells are each of internal resistance 3 ohm, right? each of resistance 3 ohm, internal resistance 3 ohm are connected so that they provide maximum current to a load, resistance 2 ohm, right? We know that the maximum current occurs, or the maximum power across the load is only possible when the resistance of the load is equal to the internal resistance of the circuit or the cells, right? Now, there are 54 identical cells, right? There are some cells which are placed like this. There are some n number of, let's suppose n number of cells are placed in series like this, right? In a single row, right? And let's suppose there are m rows. Let's suppose there are m rows, right? There are m rows like this, and so on, right? There are m rows. And total, there are 54 cells. There are 54 cells, right? There are 54 cells. Let's suppose there are n cells in each row, right? Then the equivalent resistance of these n cells would be 3n, right? 3n, because they're in series, right? They're in series, and all these 3n resistances will be actually in parallel to these m rows, right? They will be parallel to these m rows, right? So their equivalent resistance for the whole circuit will be 3n upon m, right? It will be 3n upon m, and this should be equal to the internal resistance, that's R, right? This should be equal to the external resistor load, right? That's R, right? So the load resistance here is given as 2 ohm, right? It means the 3n upon m must be equal to 2 ohm, right? That this must be equal to 2 ohm, right? This must be equal to 2 ohm. But we have to find the number of cells in a row. We have to find the number of cells in a row, right? The 54 identical cells, each of internal resistance 3 ohm, are connected so that they provide maximum current to a load, right? They provide maximum current to a load resistance 2 ohm, right? Find number of cells in a row, right? We have to find the value of m, right? We have to find the value of m. Now we know that the product of these m rows multiplied by the number of cells in each row will give us the total number of cells, right? So if there are n cells in each row and there are m rows, then the total number of cells will be m multiplied by n. That should be equal to 54, right? That should be equal to 54, right? So m multiplied by n will be equal to 54, right? So from here, we can replace the value of n, right? We can replace the value of n by 54 upon m, right? 54 upon m. We can substitute the value of n in this above equation, that's 54 upon m square, right? That should be equal to 2, right? 54 upon m square, that should be equal to 2, right? Now from here, you can see here, it will be equal to uh, 54. The value of m square will be equal to 3 multiplied by 54 upon 2, right? Upon 2. So this comes out to be the value of m, right? Since there are m rows, right? There are m rows and the n resistances in each row, right? So there will be 3n resistance, right? Upon m, that should be equal to r, right? Now there are m rows, right? So m multiplied by n, right? M multiplied by n should be 54, right? It should be 54. And then the value of n comes out to be 54 upon m, right? 54 upon m. So it will be 3 multiplied by 54 upon 2, right? So from here it will be 2, it will be 30, 27, right? It should be 27, right? 27, right? So from here, the value of m comes out to be 3 to the power 4, right? 3 to the power 4, right? So it means the value of m will be here. That will be nothing. That will be equal to, that has to be equal to 9, right? So the value of m comes out to be equal to 9 here. So m is equal to 9. It means there are m rows. There are m rows. If the value of m is 9, then the value of n will be here 3n upon 3n should be equal to twice f, right? It means n is equal to 2m upon 3, right? That's equal to twice 9 upon 3, right? That's equal to 6, right? It means the value of n should be 6 and the number of row. Find number of cells in a row, right? In each row there will be 6 cells, right? In each row there will be 6 cells, right? And there will be 9 such rows, right? In each row there will be 6 cells, and there will be such type of such n number of 9 number of rows, right? 9 number of rows. So the value of n comes out to be 6, and the value of m comes out to be 9, right? Balanced Wheatstone bridge is shown, right? If we interchange the position of battery, right, and galvanometer, then then find the current in galvanometer, right? The Wheatstone bridge is a balanced Wheatstone bridge only when the product of these diagonally opposite resistors should be equal to the product of these two resistors, right? We can see the whether the bridge is balanced or not. So 4 multiplied by 3 is equal to 12, and 6 multiplied by 2 is also equal to 12, right? So it means that it's a balanced Wheatstone bridge, and we know balanced in case of balanced Wheatstone bridge, there is no deflection shown by the galvanometer, or the current flowing through the galvanometer is equal to 0, right? There will be zero current flowing through the galvanometer, right? Now let's look at this question, right? The figure shows part of certain circuit, right? Find uh, what we have to find in this circuit, right? Maybe we have to find the VB minus VC, right? VB or VC minus V. Let's find out the value VB minus VC, right? Or VB minus VC or VC minus VB, right? So this is the value we have to find out in this circuit, right? Now you can see here there is a three resistors, five resistors, 1 ohm, 2 ohm, 4 ohm, 6 ohm, and 5 ohm, right? The potential across these batteries is given as 12 volt, 3 volt, and the current is flowing like this, right? The current flowing through the circuit is shown, right? Now you can see here there is a current here at this point. There is a current 2 ampere, right, leaving, right, and there is a current of 4 ampere leaving. It means that the current of 6 ampere must have entered the point, right? Must have entered the point. So 6 ampere current must be entering the point, right? Now here in this case also, at this junction, at this junction, there is a 5 amperes current leaving, right? 6 amperes current leaving. Then it means that the current through this branch must be 6 plus 5. That's 11 ampere, right? If 11 amperes current actually enters the junction, then only 11 amperes of current will leave the junction, right? Now we have to find the current through the 5 ohm resistor will be nothing. It will be 11 ampere, and the current through this 2 ohm resistor here will be 6 ampere, right? Now if we have to find the value of VB minus VC, once again we'll be using the same concept, right? The concept is that we'll just replace this VC here with a battery and connect it this with ground, right? We'll just replace this with the battery here again. We'll connect it with the ground, right? And we'll apply the KCL from ground to ground. We'll apply the KVL from ground to ground, right? Now the first terminal will face here at point C will be the negative terminal, that's minus VC, right? Now that we are going against the direction of the current, so we'll take this potential drop as negative, that's minus 5 volt, right? Now we'll face the negative terminal of this 12 volt battery, that's minus 12, right? The current through this 2 ohm resistor is 6 ampere, and we are moving along the direction of the current, that will be plus 12 volt, right? That will be plus 12 volt, and we'll be facing here a positive terminal of this 3 volt battery, right? And the current through this 4 ohm resistor is 2 ampere. Will just multiply 4 with 2, right? And we'll have the positive terminal of this battery VB here. We'll write it as VB, right? That will be equal to 0. Now we have applied this KVL from ground to ground, right? From ground to ground, right? Now minus VC, right? This plus 2 and minus 2 will get cancelled. Minus 5 plus 3 will be minus 2, right? Plus 8 plus VB, that should be equal to 0, right? That should be equal to 0. So from here we have to find the value VB minus VC. So VB minus VC will be nothing. That will be equal to minus 6 volt, right? So minus 6 volt will be the answer to this question, VB minus VC, right? If we have to find the current through 5 ohm resistor, it will be 11 amperes. If the current has to be found through 2 ohm resistance, it will be 6 amperes. And if we have to find the potential differences between point C and point B, it will be minus 6 volt, right? It will be minus 6 volt. Now, in the given circuit, right? In this given circuit, we have to find the potential, right? We have to find the potential in the given circuit. We have to find the potential difference between the points P and Q, right? Between the points P and Q, right? So it means we have to find the potential difference between these two ends. It means the potential difference will be the same across these two endpoints. The potential difference will be the same across this 9 ohm resistor, right? Let's so VPQ will be nothing. It's the potential difference across the 9 ohm resistance, right? V, right? Now, to find out this VPQ, right, potential difference between P and Q, we'll just apply the KVL in this circuit, right? Applying the KVL. Now the current I is flowing through this circuit, right? Current I is flowing through this circuit. We'll face the negative terminal of this battery. We'll write it as minus 12, right? I will face the positive terminal of this battery. We'll write it as plus 8. And we have the we are moving along the direction of the current, right, in all the three resistors. So it will be 9 plus 1, that is 10, plus 12, 10 plus 2, that's 12. That will be 12 multiplied by I, that has to be equal to 0, right? So from here, minus 4 will be minus 4 plus 12 I will be equal to 0, right? So the current flowing through this circuit is nothing, it's 4 upon 12, right? That's equal to 1 upon 3 amperes, right? So 1 upon 3 amperes is the current flowing through this circuit, right? If the current flowing through this circuit is 1 by 3 amperes, then the potential difference across these two ends of the resistor will be equal to V will be equal to resistance, that's 9 ohm multiplied by the current, that's 3. So it will be 3 volts, right? If 3 volt is the potential difference across these two ends, the same potential difference should be across P and Q. It means the VPQ has to be equal to 3 volts, right? So the value of VPQ will be nothing, that will be equal to 3 volts, right? Now let's discuss this question number 16 here, right? The question number 16, for the given circuit, right, shown in the figure, the current I will be, right? So in the circuit, we have to find the current I. So the current I can be only found, right? You can easily find this current by using the KVL in the circuit, right? KVL in the circuit, or we can just find the current. These are the two batteries, right, in series with each other, right? Then their equivalent EMF we can also find, right? Or we can apply the KVL as well, right? So applying the KVL in this circuit, right? So we are moving along this direction. We'll face the positive, negative terminal of this battery, right? We will face the negative terminal of this battery, it will be minus 4. We'll once again face the negative terminal, it will be minus 2, right? Then we have the current I flowing through these resistors, and we are moving along the direction of the current I through these resistors. So the total potential drop will be here 4 plus 2, that will be 6 multiplied by I, that's equal to 0, right? So from here, the current I will be nothing, it will be 6 upon 6, that's equal to 1 ampere, right? So 1 ampere will be the current flowing through this circuit, right? So 1 ampere is the current flowing through this circuit. Let's discuss this, what we call as meter bridge, right? Meter bridge. Now we know that meter bridge works on the concept of the Wheatstone bridge, right? Works on the principle of the Wheatstone bridge, right? So circuit diagram of meter bridge is shown in figure, right? The null point is found at a distance of 40 centimeter from A, right? We know the resistance of conductor depends upon length of the conductor, right? This is the principle on which the meter bridge actually works, right? The resistance is proportional to the length of the conductor, right? So we use this concept that resistance proportional to the length of the conductor, and then we use the concept of the balancing Wheatstone bridge to calculate the resistances or the null point or the different resistances of unknown resistance, right? Now circuit diagram of meter bridge is shown in figure. The null point is a point where actually the deflection shown by the galvanometer is zero, or we can say it's a balancing condition, or the current drawn through the galvanometer is zero, right? So it's a balancing condition of the Wheatstone bridge, right? So the null point is actually found at a distance of 40 centimeter from point A, right? So at a distance of 40 centimeter from point A, the null point is there, right? The total length, total length the total length of this reached, or we can say meter bridge wire, right? That's equal to 100 centimeters, right? If now a resistance of 12 ohm, right? If now a resistance of 12 ohm is connected in parallel with S, right? It's connected in parallel with S. The null point shifts to 64 centimeter, right? The null point shifts to 64 centimeter. Determine the value of R and S, right? We have to find the value of R and S. The balancing condition of the Wheatstone bridge is R upon S, right? Should be equal to L1 upon L2. This is the balancing condition, right? Now, if L1, let's suppose L1 here is 40, right? Then L2 should be equal to 100 minus 40, right? 100 minus 40, that's 40 upon 60, right? 40 upon 60. So this is the balancing condition. Huh? Now the second condition is that if a resistance of 12 ohm is connected in parallel with S, right? A resistance of 12 ohm is connected in parallel with S, right? If we apply a resistance of 12 ohm in parallel with S, right? In parallel with S, 12 ohm resistor, right? So in that case, their equivalent resistance will be actually S into 12 upon S plus 12, right? S into 12 plus S into 12 upon S plus 12, right? In that case, the balancing condition shifts to 64 centimeter. It means the new balancing condition from A will be 64 centimeter, right? And the remaining length will be 36 centimeter, right? Now, once again, we'll be using the same condition here. R upon, we'll write it as S equivalent, right? It will be equal to L1 upon L2, right? Now, L1 is 64, L2 is 36, right? So this is the condition, right? This is the equation first, right? This is the equation second, right? This is the equation second. Now, just dividing, what we can do here, we can just divide. It will be 2 upon 3 here, right? 2 upon 3 here. So it has to be equal to 2 upon 3 here. If we divide these two terms here, right? R upon S, right? So will R and R will get cancelled. We're left with S equivalent upon S, right? That will be equal to 64 upon 36, right? Multiplied by 2, multiplied by 3, right? So it will be 12 here, right? So it will be 32 here, 32, or it will be 4, 3, 4, 8, right? So 8 upon 3, right? Will be the final ratio, 8 upon 3. So 8 upon 3 is nothing. It's actually equal to S equivalent upon S, right? So S equivalent upon S. Now S equivalent is nothing. It's 12 S upon S plus 12, right? S plus 12 upon S multiplied by S, right? S and S will get cancelled, right? So from here 8 upon 3 is nothing. It's equal to 12 upon S plus 12, right? 12 upon S plus 12, right? So from here it will be 4 2 4 3, right? 4 3. So we left with cross multiplying it 2s plus 24, right? 2s plus 24 will be equal to 9, right? So the value of s will be here nothing. That will be equal to 15 upon 2, right? 15 upon 2. So if we get the value of s, we'll get the value of R as well, right, using this equation, right? So this is how we can find the value of S and R for this Wheatstone bridge or meter bridge, right? So the condition, the only principle is that this balancing condition is satisfied at the null point by the Wheatstone, by the meter bridge, right? That's R upon S should be equal to L1 upon L2. This is the null condition or balancing condition, right? Now let's discuss this question here, right? This is the final question, right, with respect to the today's session, right? So with this question will be concluding the chapter current electricity today, right? The final question is that a resistance wire connected in the left gap of a meter bridge balances a 10 ohm resistance in the right gap at a point, right? Which divides the bridge wire in the ratio 3 ratio 2, right? If the length of the resistance wire is 1.5 meter, right? If the length of the resistance wire is 1.5 meter, then the length of one ohm of the resistance wire is. So the condition is that this x actually balances this r, or it will only balance that x upon r should be equal to L1 upon L2, right? L1 upon L2, and this ratio is given as 3 ratio 2, right? 3 upon 2. Now the value of r is given here. The value of r is given here. The value of R is given here. That's equal to 10 ohm, right? That's 10 ohm, right? So it means the value of X has to be equal to 15 ohm, right? 15 ohm, right? 15 ohm is the value of X. Now the question is that if the length of the resistance wire is 1.5 meter, right? If the length of the resistance wire is 1.5 meter, then the length of 1 ohm of the resistance wire is, right? So it means this 15 ohm should be equivalent to, right? 15 ohm should be equal to the resistance of 1.5 meter, right? 1.5 meter. Then the resistance length of the uh, then the length of the 1 ohm resistance, right? It means the 15 ohm has length equal to 1.5 meters, right? And we have to find the length of 1 ohm resistance. That's equal to 1.5 upon 15, right? 1.5 upon 15, right? So it will be actually equal to 10 to the power minus 1, right? 10 to the power minus 1. So this should be the order of the resistance, right? Equal to the 1 ohm resistance wire, right? This should be the order of the length of the wire, right? So that's it today for today, right? We're done with the current electricity chapter, right? In the next section, we'll be discussing electrostatics, right? We'll be starting with electrostatics. That will be done in the next lecture or in the next session, right? So that's it for today. We'll stop here. Meet you in the next session. Till then, take care and goodbye.